Hi, this is a remake of the problem 24 on page 92 of the Siegel book, and it says calculate the pH of a 0.2 molar solution of amine that has a pKa of 9.5. Okay, so this is a fairly easy question to answer, and I feel like the last time I said some things that were kind of confusing to people. So I'm going to try to say it a little bit clearer. So whenever I have a pKa that's greater than 7, when you have a pKa that's greater than 7, you will have acid, which is something that I think people got confused about when I was talking about in the last video that I made. You always have an acid and a base form of your compound. You're always going to have, it doesn't matter what pH is, you will always have some sort of acid and base form. However, I feel like when the pKa is greater than 7, I find it's easier to solve for the pKb. This is just from my personal experience. If you can solve it with the pKa, please do so. And the main reason for that is the pKa right now equals 9.5. What that means is that the concentration of an acid or sorry, that doesn't mean that. What that means is that this is basically 9.5 logs, negative logs, and that's kind of a lot of error that could happen. But when we look at the pKb, and to convert from pKa to pKb, we just subtract, we take 14 and subtract 9.5, and we get this. Okay. That would be this equation right here. We find that this is 4.5, which means we're only dealing with a 4.5 powers of 10, or logs, or whatever you want to call it. So that's just kind of a personal preference. So when we write out this amine, I'm going to write okay, this is going to be acid plus a base. So that's what that means. Now we have, at the very start of this, we have 0.2 molar and 0 of this and 0 of this. At the very, very beginning of this reaction, right? But at the finish, we don't know how much of this we have. And this is going to be basic stoichiometry. So one molecule of this is going to make one molecule of this and one molecule of this. So that's why these are both x. So we're just going to put in a variable because we're not sure. And then this will be 0.2 minus x. Okay. So if we do our products over reactants, this is our reactant and this is our products. So we're going to get x squared, because x times x over 0.2 minus x and 0.2 minus x. So one thing about this is that we can totally neglect our x in this sample. And the reason we can do that is because the amount of x, or whatever we're solving for, is going to be very, very, very small, right? It's going to be a lot less than 5% of 0.2. So knowing that, we can actually disregard x. And if you want to see some sort of example of this, you can actually do the what you'd have to do is you'd have to multiply whatever we're solving for. This time we're going to solve for pKa, or pKb, sorry. We're solving for pKb as a personal preference. If you want, you can multiply this by the bottom by this pKb, subtract the x squared, and do your quadratic formula, or quadratic equation. And you actually end up about 0.0001 difference. So the only real difference is you're wasting about 5 minutes of your time. So now what we're going to do is we're going to have our pKb, and we are going to make our pKb right here is 4.5. Okay. So let's rewrite everything because this looks kind of messy. Remember, we cross out the negative x because we don't care. That's going to be 4.5. But we need this actually in, sorry, this isn't, it doesn't equal the p, it just equals the kb. So that would be, this 4.5 turns into 10 to the negative 4.5. And this turns into 10 to the negative 4.5 as being rewritten. So when we raise our value, our 10 to the negative 4.5, what we're going to get is 3.16 times 10 to the negative fifth. And then we're going to multiply 0.2 over here. So we're multiplying that to solve for x. So now we have x squared equals 6.32 times 10 to the negative 6. This is our kb. It's very important that you always write down what you're solving for at the very beginning, and always keep track of it. Okay. One thing I made, the reason I kind of pulled the video of this the first time was because I accidentally I wrote pKb, and then down here when I actually transferred the pKb into kb, I wrote Ka, and I said Ka. It was very confusing for people. So try and keep a very careful eye on what you're solving for. So we are solving, this is our Kb, and this is OH, negative OH. Okay. So now we're going to take the square root . And that's going to give us 0.0025, right? But so this is the concentration of our OH. So what we need to do is we need to convert this into pH. But first, we need to convert it to pOH, then we can convert it back into pH. My screen went blank there for a second, so hopefully we got all that. Okay. So first we're converting to pH, which is going to be the log of the answer, or the negative log. The negative log of this is going to be negative log of 0.0025 is going to equal 2.6, I believe. Yep. This is our pOH, and then we're going to solve for pH. So pH will equal 14 minus 2.6. Your final pH is going to equal 11.4. So one thing that the Siegel books, and that's going to be this equation here. And yeah. So one thing that the Siegel book does is it always likes to combine more than one formulas. So whenever you're doing problems for the Siegel book, try and think about doing more than one thing. As far as in the very early problems when they first set it up, you're just going to be doing the negative log of some number. When you get into harder problems, kind of like this one, you're actually going to be doing multiple steps and using multiple formulas. So if you can't get it right, write out all your variables and all your pathways that you can get from point A to point B. So in this case, we actually to get to from point A to point B, we had to convert from our pKa into our pKb, use our stoichiometry formula, plug that in, solve for our OH concentration. Once we knew our pOH, we can convert it into pH, and we get our answer of 11.4 as our pH.